We're now going to take a look at how we write and balance chemical equations for chemical reactions. And a very commonly used abbreviation for reactions is RXN. You'll be seeing that throughout the rest of this semester. This information is found in the Chem 2A text, Chapter 7, Section 7.1, and in the Chem 22 text, Chapter 7, Section 7.3 and 7.4. Okay, so how do we write a balanced chemical equation for a chemical reaction? And recall that another name for a chemical reaction is a chemical change. So we're looking and examining substances changing, bonding arrangements, and turning from one type of substance with a characteristic set of physical properties and chemical properties. As a result of the reaction, you form new substances with their own specific composition and their own set of physical and chemical properties. In general, when you write a chemical reaction, the format is to always put the reactants, which are the starting substances, on the left side of the arrow. The arrow means that these starting substances will react to make or to produce your ending substances known as the product. You also have the option of indicating the physical state that the reactant and products are found in, the S indicating solid, the L liquid, the G gas, and the AQ meaning dissolved in water and aqueous. So let's take a look at a couple of examples of how to write the balanced chemical equation for a reaction. The first one, we're asked to write the balanced chemical equation for the combustion of methane, which is the major product or major substance, in natural gas. So write the equation for the combustion of methane, one reactant, with oxygen gas present in the atmosphere, our second reactant, and the reaction produces carbon dioxide and water vapor as our only products. So how do we write the balanced chemical equation for this reaction, this chemical change? Step 1 says to write the correct chemical formulas for reactants and products. And so right away we see that we need all of those skills and tools we learned with nomenclature, how to write the correct formula for a substance. So we need to remember our nomenclature rules, and we also need to remember which elements are found in nature as diatomic elements. And a reminder to you that those diatomic elements are located on the periodic table in the shape of an upside down L, nitrogen, oxygen, and all of the halogen family, as well as the element hydrogen. They are found in their elemental state as diatomic molecules. So looking at this problem, I see that we have to write the chemical formulas for our first reactant, methane. And remember, methane is one of those names that is not systematic, but that you need to be able to know the formula for, along with water and with ammonia. So chemical formula for methane is CH4, and it is the major substance found in natural gas. So we'll put that little G subscript there indicating that it's in the gaseous state. And we are reacting it with oxygen in the atmosphere. And oxygen is one of those diatomic elements. So I'm going to put the little O2 there indicating diatomic oxygen molecules, also of course a gas. And our products are carbon dioxide, molecular substance, CO2 gas, plus, and then we have water as a vapor, meaning water itself is in the gaseous state. And moving this plus sign over, giving me a little more room here. So we have completed step 1. We have written the correct chemical formulas for the reactants and the products. Now in our second step, what do we need to do? Well, we need to count the total number of atoms of each type of element on both sides of the reaction arrow. In other words, the reactant and the product side. And our goal is to try to balance or make that total count equal on both sides of the arrow. In other words, we have to satisfy the law of conservation of mass. Law of conservation of mass, which says that in a chemical reaction, matter is neither created nor destroyed, right? It merely undergoes rearrangement. The atoms of elements rearrange and form new bonding arrangements to make new substances. So we have to count the total number of atoms of each element on both sides of the arrow, and then we're going to place small whole number values that we call coefficients in front of each formula to balance the total number of each type of atom on the reactant and the product side. And notice that you can use fractions as temporary coefficients to help balance, but in the end you must convert those fractions into whole numbers. So let's go ahead and take a look at the count here. I see that I have 1 carbon on the reactant side, 1 carbon on the product side, so I can make that notation. 1 carbon, 1 carbon. I see that I have 2 oxygen. Oh, let's finish the hydrogen here, sorry. I see that the formula of methane has 4 hydrogen. And looking at this product side, I see that I have 2 hydrogen present here. I'm just going to try to line these up because I don't have a lot of room. So 1 carbon on the reactant side, 1 carbon on the product side, 4 hydrogen total on the reactant side, 2 hydrogen in the form of water on the product side, and then I see that I have 2 oxygen on the reactant side and a total of 3 oxygen on the product side. So right away I see that my equation is not balanced. I do not have equal numbers of each type of atom present on each side of the arrow. My carbon is balanced, so I'm going to have to look at hydrogen. 4 hydrogen atoms on the reactant side, only 2 hydrogen atoms on the product side. So I am going to come and put the whole number coefficient 2 in front of the water. That will now give me a total of 4 hydrogen on the reactant side, and that now changes my oxygen count. 2 times 1 is 2 plus 2. It now changes my oxygen count to a total of 4. And it's okay, we can use that in blue. Okay, well let's come over here to the reactant side. I did balance the hydrogen, but I see that my oxygen is not in balance. So I am going to put a whole number coefficient 2 in front of the oxygen on the reactant side. And now this changes the total number of oxygen atoms to 4. So looking at my total count here to check that I have equal numbers of all types of atoms on both sides of the arrow, I see I have 1 carbon on each side of the arrow. I see that I have a total of 4 hydrogen, 2 times 2, 4 hydrogen on the product side, and I see 2 times 2, 4 oxygen on the reactant side. 2 times 1 is 2 plus 2, 4 oxygen on the product side. So I have satisfactorily written the balanced chemical equation for the combustion reaction of methane with oxygen gas. Let's do one more example which illustrates how fractions can be useful in helping to balance an equation. So this example number 2 states to write the balanced chemical equation for the combustion of pentanol. Now pentanol is an organic substance. I don't expect that you know the formula of pentanol based on its name. You would have to have some organic chemistry instruction in it in order to be able to do that. But if I provide you the correct chemical formula, you should be able to put it into the equation. So we're looking at the combustion of pentanol with oxygen gas producing carbon dioxide and water. So you can see here that I kind of was trying to make efficient use of the equation that I have already written here. I'm going to change this notation to example 2. I see that oxygen is a reactant, carbon dioxide and water are our products. So then I can easily here come in and erase minimally and start all over again with example number 2. So I'm trying to be efficient with the writing that I have here up on the board. So I've erased methane and I am going to put in the chemical formula for pentanol, C5H11OH. Now pentanol is going to be a liquid, not a gas at room temperature, so I'm going to make that notation. So pentanol is reacting with oxygen. Whenever you have a combustion reaction occurring, one of the reactants is always oxygen present in the atmosphere, undergoing reaction with whatever the fuel is, the substance that is burning. And whenever you're burning a carbon-based fuel, you will always get carbon dioxide and water as your products. So we have the correct formulas, and now we need to begin doing the counting. I see that I have a total of 5 carbon atoms on the reactant side. So I'm putting 5 carbon atoms. I see 11 hydrogen, but there is another hydrogen here, and you may wonder why are those hydrogens separated and split apart. That has to do with concepts in organic chemistry that, should you go on, you will be introduced to. But nonetheless, we can count 11 plus 1, giving us 12 hydrogen, and then 2 oxygen here, but there is also an oxygen in the formula of pentanol, so that's giving us a total count of 3 oxygen on our reactant side. Doing the same process on the product side, I count 1 carbon, I count 2 hydrogen, and I count 3 oxygen. And let's put that dash here so it's clear. We're talking about elements. Oh, and let's put the C here, indicating 1 carbon, 2 hydrogen, and 3 oxygen for our counts of elements on the product side. Okay, what to balance first? And this is a trial and error process. In other words, there's no one set process that works for every type of chemical equation. So trial and error, you put in coefficients, see if they work. But here is a suggested order that may be useful. Try balancing metals first. So metals first, then non-metals, and save hydrogen and oxygen for the last elements to try to balance. So I don't see any metals in this chemical equation, so I'm going to jump in and start with carbon, save hydrogen and oxygen for last, and I'm going to save oxygen for the very last in this example because I see it by itself as an element, so any coefficient I've put in front of the formula for oxygen is not going to alter the count for any other element. So it's useful if you have something as an elemental state, especially oxygen, right, to save oxygen there for the last. Right, so 5 carbon on the reactant side. I'm going to come and I am going to put a coefficient 5 in front of the carbon dioxide, and immediately I have balanced the carbon atoms with 5 carbon atoms on each side. But that changes my oxygen count. My oxygen count now changes to a total of 11. Right, so I have to keep a running count of what's changing. Now let's take a look at the hydrogen count. 12 hydrogen on the reactant side, so I am going to come and put a 6 coefficient in front of the water so that I now have 12 hydrogen on the product side, but again, that changes my oxygen count. 5 times 2 is 10, plus 6 times 1 is 6. That changes my oxygen count to now 16 oxygen on the product side. Now, a very, very common error that is made here at this point is for students to come, take a look at this elemental oxygen, and put a number 8 in front of it. Going 8 times 2, 16. They think that they have now balanced the equation with total equal numbers of all types of atoms on both sides of the error, but can you see the mistake here? This equation is not balanced. 8 times 2 is 16, but there is also an additional oxygen present in the pentanol formula. This count is 17 oxygen atoms, and we're out of balance with our oxygen. And so what do you do when you reach this point? You thought you've balanced, but it is in fact out of balance. Here is when a little trick involving fractions could be useful. What I really need here is for this total oxygen count from this elemental oxygen to add up to 15, because 15 plus 1 is 16, and then I would be in balance. So there is no whole number that multiplied by 2 is 15. Anything times 2 is an even number, but I can use a fraction. I need the number 15, so the number I need, I put over 2, because then I'm going to have to multiply by 2. So 15 halves, 15 divided by 2, multiplied by 2 is 15. And then 15 plus 1 is 16. So right now, my equation is balanced. Note that if no coefficient, no number is written in front of a formula, it is understood to be the number 1. But by convention, we don't write the number 1s in the equation as coefficients. We leave them unwritten, and it is understood that the coefficient is 1. So my equation is balanced right now. I have 5 oxygen, 12 hydrogen, 15 over 2 times 2, plus 1 is 16 oxygen. And I see the same count on the product side, 5 carbon, 6 times 2, 12 hydrogen, 5 times 2 is 10, plus 6, 16 oxygen. I told you you can use fractions to help balance, but you have to convert those fractions into whole numbers. So how do you do that? Well, we're going to have to multiply all of the coefficients through, right, by 2. And why by 2? Because we're trying to get rid of that 2 in the denominator of the 15 halves. So when we multiply everything through by 2, that's going to give us a final coefficient of 2 for the pentanol, 15 for the oxygen, 10 for the carbon dioxide, and 12 for the water. These will be our final coefficients when we multiply every single coefficient through by 2 to maintain the equality. So just showing that here and cleaning this up, so I'm going to write in my final coefficients in front of the formula of 2, 15, 10, and 12. And now we'll do one last check here to make sure that we are looking at a balanced chemical equation. So 2 times 5 is now 10 oxygen. 11 plus 1 is 12 times 2, 24 hydrogen. 15 times 2 is 30. 2 times 1 is 1. So 32 oxygen. On our reactant side, 10 times 2, right? 10 times 1, sorry, jumping ahead, 10 times 1, 10 carbon, 12 times 2, 24 hydrogen, and then finally our oxygen count, 10 times 2 is 20 oxygen, 12 times 1 is 12, and 20 plus 12 is 32 oxygen. So, looking at what we have here, I see that I have balanced the total number of atoms of each type of element on each side of the arrow.